talked about odd and even and like maxes and mins and increasing and decreasing, right? That sounds about right. If anybody, I think we'd assigned up through 22. If anybody has any questions about any of that, we can deal with that here to start. Landon? 21. So on these questions, we're asking to basically prove whether these things are odd or even or neither. So here our function is g of x equals 1 over x. So I'm going to use, for all of these, we'd start with evaluating the...
I left my keys in my car, so the police have to come
Oh,
get it
no.
out. So they told me to not mark me at X. So
Okay.
I'm gonna go talk to the police.
Okay. So g of negative x is what we start with, right? And what that says is I'm going to, in my g of x, I'm going to replace all the x's with negative x's. So I really have 1 over x. And I know that with a fraction, that negative sign, I can take and kind of move it wherever I want to. So instead of leaving it in the denominator, I'm just going to move it out front. And now if I compared this to the original, well, it's not the same. So I know it's not even, right? This one is negative. But if I look at it kind of this way, where really I have like negative of 1 over x, that is the same as the original. So really I have negative g of x. And since I have g of negative x equal negative g of x, I know this then is odd. Is that okay? Cool. Anybody else? Okie dokie. So we'll move on forward. Today we're going to talk about 1.6 and start 1.7. We probably won't finish 1.7 today, but that's okay. Oh, there we are.
Sorry for the interruption, and sorry for the delay in the morning prayer. I apologize, I only announced it to Notre Dame Middle School. So if you can pause where you're at for just one moment. Notre Dame prayer. I appreciate it. In 1 Corinthians 4, verses 1 through 2, it says, "You should think of us as Christ's servants, who have been put in charge of God's secret truths. The one thing required of us is such a servant is that he be faithful to his master. Dear Father in heaven, open our hearts to see and feel how our lives have been blessed. Open our hearts to your blessings so that we may look forward in thankfulness and joy to what lies ahead. Grant that we may be faithful to what we have received from you and never again lose ourselves in the passing moment. May we hold to all you have brought to our hearts from eternity, that your name be honored and our lives shaped anew in Jesus Christ. Give us courage to overcome the evils in life and to look with joy and confident expectation to the future, when the powers of your kingdom will be more clearly revealed. Amen." Please join me in the Lord's Prayer. Our Father,
Lord
who art in heaven,
hallowed
hallowed be thy name.
Thy
Thy
kingdom
kingdom
come,
come,
thy
thy
will be done,
on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation,
but
deliver us from evil.
Amen.
Amen. Again, teacher, so I apologize. Have a great day. No thank you.
Okay. So we'll start here talking about asymptotes. If you guys remember, we talked about asymptotes last year in our Algebra 2 class. So an asymptote was like a line on a graph, like an imaginary line on the graph, that the graph approaches but doesn't cross. So looking at an example, that's bigger than I really want it. Let's say we look at a graph that looks like this. So if I were to take a look, it looks like I see a vertical asymptote here at what looks like about -3. Everybody good with that? And I see over here what looks like another vertical asymptote at what I would say is about +1. Everybody okay there? And it looks like maybe I have a horizontal asymptote kind of right here that also looks like at about 1. You guys all buy that? So let's see what we say. -3, +1, and +1. Now this horizontal asymptote is not technically an asymptote. Can anybody see why it's not? Landon? Yeah, so if we look at the middle part of the graph, you can see that the graph does cross the asymptote here. In your Algebra 2 class last year, you might have used the less specific term end behavior to describe something like this. So like all asymptotes are end behaviors, but not all end behaviors are asymptotes, right? The asymptote is the more specific because you can't cross it. But if we look at the ends of this here, it does look like we have the approaching part. As x gets very small or x gets very big. For this section, we're going to still refer to something like this as an asymptote. We'll differentiate between asymptotes and end behavior in the future. But for just simplicity's sake, we're just going to call this still refer to this kind of thing as an asymptote for right now. Everybody's okay with that so far? Okay. So the function that gives us the graph above is this. This is an example of a rational function. And rational functions also often have vertical and horizontal asymptotes. Do you guys remember the way last year that we found the vertical asymptotes for a rational function like this? Okay. The way we did this was by taking the reduced denominator, setting it equal to 0, and solving. So the first thing I want to do is check to see if I can reduce this fraction. To be able to reduce this fraction, I'd have to be able to factor the numerator and denominator, right? So I notice the numerator and denominator are both quadratics. Everybody's okay with that? Okay. And it's nice because both of these quadratics in the numerator and denominator have a leading coefficient of 1. So if I can factor them, I can use the fast factoring to do it. So let's look at the numerator first. I'm going to see if I can find two numbers that multiply to give me -3, and then also add to give me +3. Are there two integers that are going to do that? The answer should be no, right? The only pairs of numbers that multiply to give you -3 are 1 and -3 or -1 and +3, neither of which are adding to give you +3. Everybody's good? So the top isn't going to factor. So there's no reducing that can happen if I can't factor one part of the fraction, right? So I don't need to even worry about any more factoring per se. So I'm just going to take the denominator then and set it equal to 0. What I have then is a quadratic equation. So I notice this quadratic equation has both x squareds and x's. Everybody see that? In this sort of situation, we really have only two choices on how to solve this. I can either factor it, or I can use the quadratic formula. Now, not every quadratic would be factorable, but if I can factor it, it's usually easier than using the quadratic formula. So that's the method that I would choose to use to try to solve this. So once again, I'm going to ask if I can find two numbers that multiply to give me -3 and add to give me +2. Here, the answer is yes, we do have the two numbers. Landon, what are they? 3 and -1. So I can write x plus 3 and x minus 1. And then using the zero product property, I can set each of these equal to 0 and solve. And I notice here that these match the vertical asymptotes we observed in the graph. Everybody okay with remembering doing that? Not terribly complicated, right? How about finding the horizontal asymptote? This was harder, right? If you remember, there was like a couple of different cases, and they had to do with the degrees of the numerator and denominator, and if they were, whether the two degrees were, one was bigger than the other, or they were equal, or which one was bigger than the other one, and it was kind of a mess. What we're going to do instead is we're going to just kind of verify what we're looking at on the graph numerically. So what we're going to do is we're going to just pick some progressively bigger and smaller values of x and confirm that the y values we're getting are approaching but not crossing the asymptote that we think we see. So I'm going to just use the x values of 10, 100, and 1,000, and -10, -100, and -1,000. I'm going to plug those in for the x's in my function and see what kind of y I get, just to make sure that that y value is always staying on the same side of 1, which appears to be my asymptote. Everybody okay with that plan? So I'm going to use my calculator to do this. The easiest way to probably do this is I'm going to go to the y equals menu, and I'm going to type in my function exactly as it's written, except I'm going to make sure I put a parenthesis around the entire numerator when I type it in, and then I'll use the division symbol, and then put a parenthesis around the entire denominator when I type it in. Okay, when you're typing in a fraction into your calculator like this, you got to make sure you put parentheses around the entire numerator and the entire denominator if those numerator and denominator contain like more than one term, if there's addition and subtraction going on in them. You might also be tempted to use the fraction shortcut command that we had talked about last year on your calculator. I would not use it in this case because one of the quirks of that function is it's going to give you a fraction back. And it's not so easy to look at a fraction and tell like what the decimal is to see how close it's getting to 1. You know what I mean? So, looking at 2006 over 2007, I can't tell if that's really closer to 1 than like 1562 over 1563. It's like, okay, is that closer or not closer? I'm not really sure. I'd rather have the decimal. Everybody's good with typing this in? What I'm going to do next is I'm going to go to my window, and I'm going to update the x min and x max so that they contain the smallest and largest x values that I plan to type in. Okay, so since I was going to use the x values from -10 to -1000, my x min should be -1000, and because I'm going to use the x's from +10 to +1000, I'm going to pick my x max to be 1000. And realistically, you can probably use these same x's every time. There's nothing magic about them. They're just easy ones to do. Everybody's okay? Okay. Once I've made that update, I'm going to go ahead and hit graph. So my graph is this really unimpressive looking horizontal line, mostly just because I'm so far zoomed out. If I change my window to where I wasn't going from -1000 to +1000 and pick something a little bit more reasonable, I'd have a better picture. So what I'm going to do then is I'm going to press second and the trace button and pick the value command. What the value command does is now it's going to prompt me to type in a value for x, like -10. And when I press enter, it gives me the y coordinate to go along with that. So I'm just going to kind of record this information. And I think 3 decimal places is probably sufficient. I'll do it again, this time with -100. So that's 0.989. And then again with -1000. Oops. So that's 0.998. And you can see that each time we're getting a little bit closer to 1, but we never cross 1. Worth pointing out when I'm using this value command, if I pick a value that's referring to a point that's not on my screen, like if I tried to do value or x equals -1001, it gives me an error because I'm picking an x value that's not on the graph that I can see, right? I mean, that corresponds to a point on the function, but it can't see it on the graph, so it can't. The value has to be able to see the point on the screen to be able to give it to you. You know what I mean? That's why we changed our window before we hit graph. Everybody okay? Just giving you a troubleshooting, because that's probably almost all of us were going to make that goof see at some point. And I'll do the same thing for +10, +100, and +1000. So here I have 1.085. And then I got for 100, 1.009. And then for 1,000, I have 1.00009. And again, I see the same sort of behavior, right? So all of this tells me that that horizontal asymptote that I observed at 1 seems to be correct. Everybody's okay with that? Victoria? What did I do for it?
Yeah.
So the window I chose was this. I just needed to make sure the smallest value that I was going to plug in was my x min, and the biggest value I was going to plug in was my x max. Okay? And that's the gist of this section, really. The only thing or what I'm trying to take away is that you can look at a graph and pick up the asymptotes from looking at the picture. And then you can confirm that your observations are correct by either, in the case of a vertical asymptote, setting the denominator equal to 0 and solving. I should say the reduced denominator equal to 0 and solving. Or in the case of a horizontal asymptote, confirm that numerically by pulling some progressively larger x values from the function and finding their corresponding y values. And show that that does show the approach but not crossing behavior that we're looking for. Is that okay? Cool. Next up, we'll talk about function operations. So we'll start with the definition. So let f and g be functions with intersecting domains we require that condition that the domains be intersecting, so that if you plug an x into f and you plug an x into g, you get an answer for each of them. They're not undefined, right? So that's all that intersecting domains piece is, just so that you can actually evaluate each of them with the x's you're using, so that the problem is even like possible to talk about doing. That's all. Then for all values of x in the intersection, we define the sum of the functions f and g evaluated at x to be f of x plus g of x. So if I want to look at the sum of two functions evaluated at some value x, I can just find this f of x and g of x and then add them together. So I can do the evaluation before I do the addition. So difference, same idea, f minus g of x equals f of x minus g of x. And we have multiplication, so the product f times g of x, again, is equal to f of x times g of x. And then our last of our basic operations, the quotient, which corresponds to division. So f divided by g of x is equal to f of x over g of x, provided that g of x is non-zero. Why does g of x have to be non-zero for this quotient? It's the denominator of a fraction, right? Can't divide by 0. That has no answer. That's undefined. So that's the only reason why g of x can't be 0 for the division case. Is that okay? So again, nothing surprising here, that this works exactly as we'd hope. That instead of doing having to do the addition and then evaluate, we can actually evaluate and then do the addition, which makes life much easier. So let's look at an example. So let's say f of x is just like the function 2x minus 3. And let's say g of x is the function square root of x plus 2. And then let's say we want to do f plus g of x. Well, from our definition above, f plus g of x is f of x plus g of x, right? Everybody's happy with that? And in the problem, we know that f of x is equal to 2x minus 3. And we know that g of x is equal to x plus 2. So let's go ahead and replace f of x with 2x minus 3 and g of x with square root x plus 2. And then the last thing I would need to do here is just any simplification or combining of like terms that's possible. Now, if I look at this 2x minus 3 plus the square root of x plus 2, is there anything I can combine here or any simplifying I can do? Can I add the 2x and the x? They're like terms, but I can't add them together. Why not? Because the x is under that square root, right? You can't take something outside a square root and combine it with something underneath a square root. We know we're not allowed to do that because the order of operations says we'd have to deal with the square root before we could do that addition. Everybody's okay with that? Can I combine the 2x and the negative 3? Well, no, they're not like terms. Neither one is under the square root, so potentially we could combine them. But I know that x's and constants aren't like terms, so those can't go together. So is there anything to do here at all? No. This is as good as it gets. So we're finished. What if we do g minus f of x? Let's do that one next. Okay, from our definition, I know that g minus f of x is the same as g of x minus f of x. Everybody happy with that? And then we can go ahead and replace g of x with square root x plus 2. And then I'll write my subtraction symbol, and then I can replace f of x with 2x minus 3. Does that all look right to you guys? Oh, it's disappointing because it's not correct. I've made a mistake here. I've made it intentionally because this is probably a mistake I would say 2/3 or maybe more of us would make on a rather consistent basis. Landon, do you see the mistake?
Are you supposed to make that positive?
Yeah, so the negative sign in front of the f of x applies to the entire f of x. So we'd really have to make sure that we're distributing that negative across the entire f of x. So as Landon said, the 3 should be positive at the end. Now that's a mistake that, at least without reminding you about this, I would expect probably 2/3 or more of us to make. Now that I've shown it to you guys and reminded you about it, I would hope that much fewer of us than the majority make that mistake, but probably still somebody's going to do it. Try not to be that person, though, right? It's not something that we're unaware of. Like, as soon as we did it, you're like, oh, yeah, I knew that. It's just one of those things we have to be kind of cautious about. Now let's do g times g of x. So again, based on our definition, that's the same thing as g of x times g of x. And since g of x is just the square root of x plus 2, I can make that substitution. What do I get when I multiply the square root of x plus 2 times the square root of x plus 2? Well, let's simplify this down a little bit, or simplify this a little bit. Ask an easier question then. What do I get if I have a times a? A squared, right? So if I have the square root of x plus 2 times the square root of x plus 2, I have the square root of x plus 2 squared. Everybody buy that? And then what do I know about the relationship between squares and square roots? They cancel each other out. So the squared and the square root can cancel each other out, and we're left with just x plus 2. And obviously there's no more simplifying I can do at that step. I guess I neglected to say at the previous step there's obviously no more simplifying we could do at that point, because it's really was kind of the same answer as the previous one, right? It's not the exact same, but it's like has all the same issues as to why you couldn't simplify it as the previous one. I neglected to mention that we were finished at that point, which is my fault. Let's say our last example here is going to be f over g of x. Again, using our definition from before, that's going to be the same thing as f of x over g of x. And I know that f of x is 2x minus 3, and g of x is the square root of x plus 2. Okay. Any simplification I should do here? Do you guys like that square root in the denominator? right? That was one of those things last year I think we talked about, that we don't want to leave the square root in the denominator of a fraction. That rule starts to fade the further into mathematics you get. For this class, what I would say is that we don't want to leave the square root in the denominator of a fraction if it's a square root of a constant. So if it was like square root 2 in the denominator, we wouldn't want to leave that. But if it's the square root of a variable or a variable expression, we're not going to care. So we're just going to say this guy is okay for us. So like what I'm saying is, if you had 3 over the square root of 2, that we would want to rationalize. But if we had the square root of 3 over x plus 2, that we're going to leave because of the variable still in there. Is that clear enough for you guys in terms of like when we need to worry about getting that radical out of the denominator and when we're not going to? If it's not, feel free to ask again, or we can talk about it more right now and clarify, but it won't come up for a little while. So we can always revisit it then. So these first 4 function operations like a piece of beard hair in my mouth or something. These first 4 function operations are the 4 basic ones, right? Because these are still the same operations we can perform with just numbers, right? We can add, subtract, multiply, and divide numbers. We can add, subtract, multiply, and divide functions. There's a 5th operation that we can do on functions that doesn't have an analog to real numbers. We talked about that operation last year also, but let's define it again right now. This operation is called composition. So let f and g be 2 functions such that the domain of f intersects the range of g we say that the composition f of g which we denote as this. So this symbol here is not the letter O. That's like the multiplication dot, but instead we write it with an open circle. So when we read that as like f compose g of x. Please, for the love of everything holy, when you see that, don't say fog. It makes me want to stab myself in the ear, and I don't want to have to go to the hospital because somebody said fog one too many times and I just snapped. Okay? That is not the letter O. That is like an open multiplication dot. I have to draw it a little bit bigger to draw it open on my sheet of paper. But I want to be clear, there's no fog at any point or any goff if I wrote them in the opposite order. You read that as like F compose G or G compose F, depending on the order that you've written it. Okay. And the way we do this composition is we do f of g of x. So let's do a couple of examples here. So we'll make up a f of x and a g of x. And we'll run through a couple of examples. So let's do f compose g of x. From our definition, we know that that's the same thing as f of g of x. What I'll do now is, since I know g of x is equal to negative 3x plus 4, I'll replace the g of x with the expression negative 3x plus 4. And when I have a function like f and then a parenthesis with stuff inside of it written after the f, I know what the instruction is telling me is to plug that stuff into the function f wherever I have x's. So basically what I'm going to do is I'm going to take this stuff and replace the x's with it, right? So I still have the 2, but then instead of the x, I'm going to write negative 3x plus 4, and then write the squared, write the subtraction, write the 3, but then instead of the x, I'm going to write negative 3x plus 4. Is everybody okay with how we did that composition? So now we need to simplify. What's the first thing I should do according to the order of operations here to simplify this expression? Anybody? So when we say parentheses, we mean the stuff going on inside the parentheses. So if you look inside the parentheses, it's just negative 3x plus 4. And those can't combine in any way. So there's nothing to do with the parenthesis. What comes next in the order of operations? Exponent. And we have one of those, right? So that should be the first thing I handle is the exponent. So how do I simplify negative 3x plus 4 squared? Who thinks it's 9x squared plus 16? Wrong F word, not the other F word. Foil it, yes, very good. So you'd have to foil that out. So really, that negative 3x plus 4 squared really means negative 3x plus 4 times negative 3x plus 4. Everybody's okay with that? And my suggestion to you, or my preference, is I'm going to do the foiling first, and then I'll distribute the 2 through after. The number one mistake I see students make is they do something like this, which is not how we multiply 3 things together. Right? If I had like 2 times 3 times 4, you wouldn't multiply the 2 to the 3 and then to the 4. Right? Yeah. Anyways, so we FOIL. So first, that's 9x squared. Outer, that's negative 12x. Inner, negative 12x. And last, that's 16. And I can combine the negative 12x's pause here as I just wrote down a lot of stuff for those of you that are following along, taking notes. That may be a little bit of catching up to do there. Gives me an opportunity to get a little bit more soda pop in at 8:30 in the morning. It's how I make it through the day. Don't judge me. I said not to judge me. Okay, just checking if you're awake. All right, next up, now that we've done that foiling out and recombined our like terms, what should I do next? We took care of the exponents. Next comes multiplication. So there's distributing that I can do here and then here. Everybody's good with that? When I distribute, I'm going to distribute the -3 and not just a 3. So -3 times -3x becomes positive 9x. And -3 times positive 4 becomes -12. And then we can combine like terms here. So -48x plus 9x becomes -39x. And 32 minus 12 becomes 20. And no more like terms to combine. So we're done. I want to point out to you that we're done with the composition here at this step. Everything after that was just simplifying, right? So just to be clear, composition is not always going to be that tedious. The actual composition was pretty easy to do. It was just kind of the cleaning up our mess afterwards that was the time-consuming part. Okay, let's look at what G compose F is. So if this was an addition problem, we would expect to get the same answer that we just got before, right? That property where the order of the operation doesn't matter, whether you do F plus G or G plus F, you get the same answer, is called a commutative property. Composition is going to be one of the few operations that we see that is not commutative. So this is not going to give us the same answer that we got before. And we'll see that pretty quickly. So by definition, G compose F of X is going to be G of F of X. My first step will be to replace F of X with the definition that we gave for that function was 2x squared minus 3x. And then what G of 2x cubed minus 3x, 2x squared minus 3x says is I'm going to take this function and I'm going to substitute it in for the x's in G. So I'm going to have -3, and then instead of x, I'm going to have 2x squared minus 3x. And then I have the plus 4. Whoa. That's going to be a heck of a lot easier to simplify than what we had last time, right? It's nice because there's no foiling we have to do. Really, the first thing I should do is just to, distribute that -3 through. And then there's not even any like terms to combine at the end. So I'm done. Again, the big takeaway here, though, is these are not the same answer. So again, the big takeaway is that that order that we do the composition definitely matters. We do not get the same answer both times. Is everybody cool? Okay. When we do get the same answer both ways, that's a very special situation. And if we get the same answer both ways and the answer is one answer in particular, that is an ultra special situation that we're going to give a name to and define right now. So if we let f and g be two functions, we say that g is the inverse function of f if and only if that f compose g of x is equal to g compose f of x, which gives us x. So we'll come back and show you guys how we can use that here in a moment. But this is a way that we can verify that two functions are inverses. But let's talk about finding inverses in general first. So let's say that we have this function f, where 1 goes to 4, 2 goes to 6, and 3 goes to 5. What is the inverse for this function going to equal? Or what would this inverse function look like? Well, here, the domain or the range from f, I'm going to use as the domain, and the domain from f is going to be the range. And then I'm just going to reverse the direction of the arrows. So instead of 1 going to 4, 4 is going to go to 1. Instead of 3 going to 5, 5 is going to go to 3. Instead of 2 going to 6, 6 is going to go to 2. And the name that I'll give this function is f inverse. Is that okay? So basically f inverse is just undoing everything that f did. Right? It's like if you think about driving from your house to your friend's house, and now you want to go back to your house, you take the same path you took to get to your friend's house, you just go in the opposite directions on things, right? You retrace your steps. Same idea here. What if your function f of x was given by like a set of ordered pairs? Well, we want to follow the same notion, right? We want to retrace our steps. So the first point, negative 2, 4, is saying that negative 2 is going to 4. If we want to reverse that, we would say that 4 needs to go to negative 2. Similarly, 6 would need to go to negative 1. 8 would need to go to 3, and then 8 should also go to 5. Do you notice something odd about F inverse in this situation, though? I have one input that's going to two different outputs. What can we say about F inverse here? It's not a function, right? Soon as you see that repeated x coordinate, an input or a domain that's used more than once, you know we got problems, right? So this leads to the question, or the observation here maybe first, that sometimes when we find these inverses, they're a function, right? Like we did in the first example. And sometimes these inverses won't be a function, like in the second example. What we'd like to do is think a little bit about this and see if we can come up with a way to predict when we're going to have a function and when we're not. So before we can do that, we're going to have to define a couple of terms. So the first term is going to be this term called onto. We say a function is considered onto, or the alternative word for onto is surjective. These two things could be used interchangeably. Onto is probably the one that would be used more frequently, but surjective is probably used, I don't know, a third of the time in resources you might look at. We say that a function is considered onto if every element in the range is mapped to by some element from the domain. So if we have, some mapping diagram for a function, this is still a function, right? Each of the inputs go to just one location, but it's not onto because nothing mapped to 4. Is everybody okay with that idea? What would this look like graphically? If you have a function whose range is not all real numbers, that function can't be onto, right? Like there's a whole mess of y coordinates that don't get used down here. So again, this is an example of a function that is not onto. Everybody okay with that? Okay. Our next definition, we say a function is considered one-to-one. Or the alternative word there is injective. Again, one-to-one is probably the more common one. And we say we're injective if every element in the domain maps to a unique a unique element in the range. So if I look at this previous example that we did, we can also say that this is not one-to-one because 5 is arranged for multiple x's, right? Basically, one-to-one is just making sure that the y coordinates, the ranges, are used only one time. Everybody's okay with that? I can see that if I look at the graph, graphically what this is going to look like. Again, this is not one-to-one. Because if I take like this horizontal line, this is the same y coordinate on the entire horizontal line. I see that I have at least 2 x's that are used. So I know this also is not one-to-one. Rather than redrawing these examples, I just figured I'd come back to them. Okay. Our last definition here is bijective. And we say a function is considered bijective if it's both one-to-one and onto. And the big takeaway here is that what else we're supposed to be doing here. That if your function is bijective, then f inverse is a function. So that's the big one there. Doesn't mean that, note that this is not an if and only if situation, right? This just guarantees that if your function is bijective, its inverse will be a function. It doesn't necessarily say that if f of x is not bijective, that f inverse can't be a function, right? All it's doing is guaranteeing you that if you have this condition, then you get that result. If you don't have that condition, if f isn't bijective, maybe its inverse will be a function, or maybe it won't, right? It's not an if and only if situation here, okay? Is everybody okay with that? I just wanted to make sure that that point is clear. This feels like a good place to stop, though we still have a bit more to do in this section, but this feels like a good place to stop. Just FYI, so we can do, I'm going to write down, this is the homework set for 1.6 and 1.7. We haven't finished 1.7. But you can probably do up through 38, probably. Is probably all realistic to do. Again, the way I've been doing your homework on My Notre Dame, just to make sure everybody can kind of see things. So, go away. So the way I'm going to do your homework on My Notre Dame, so we had 19 through 22, which was the first part of this next homework check. Rather than making a second assignment when I add to it, I'm just going to update that, to be through 56 or whatever. Is that okay with you guys? I just wanted to make sure that you guys know where to look for the homework, that I'm not going to be, every time I update something, it's just going to be updating the title, so it just shows up in your assignment library or whatever. Tyler?
On My Notre Dame, it says it's due yesterday.
Okay, well, I'll fix that. Well, no. You had 1 through 18 should have been due yesterday.
It says 13 through 22 is due yesterday.
Let me look. It's probably something I don't know. Yeah, that's fine. Save that. All right. So let's look here. let's look at this. That's probably, yes. So that's what that should have been. Okay. Okay. So that got rid of that, right? I think we're good now. Okay. So thank you. Again, if you see something funny going on, let me know. Still getting used to using this as a two-wayer thing. You know what I mean? Last year, I typically didn't put things in until I was ready to grade them. On this, I just did everything through PowerSchool. But now this is serving both functions, so it's still kind of getting used to making sure I've checked all the boxes and everything, or unchecked the boxes, or whatever's. Okay. Yeah.